All right, good morning, everyone. We still have about another minute. I want to have you get your textbook if you can. We're going to not use it extensively, but there are some tables in the back of the book that I want to introduce that we're going to work on a lot more starting next week. So if you can, please grab your textbooks. Okay, so hopefully everybody has access to their textbook. If you don't, that's no big deal. We're going to start chapter 3 a little bit today, and then we have the exam on Friday, this Friday, February 5th. The exam is in person. We're going to spread out. There will be dividers. This Friday in person at the normal class time in Holmes Hall 147, which is the big open lecture hall on the first floor. So our exam 1 will be there this Friday. Wednesday, I'll be doing an exam review. And then today I'm going to be introducing, so this is the only lecture this week, and it will not be including this lecture. This lecture is kind of an introductory lecture, and some of it is, so it won't really be covering this lecture. So everything up until right now, it will be covering, and I will go through it more in the review on Wednesday on Zoom. The exam that I have right now is 5 questions long. 3 or 4 of those are working questions like you have on your homework or the example problems that I'm doing. And 2 of those are more conceptual, what is this type questions where you don't have to use any equations. I'm still working on the exam, so I'll tell you for sure on Wednesday, but that's what I have right now. Okay. Are there any questions about anything before we get started? So we're still, I'm not working on anything in the book exactly right now, but we're going to be looking at the book in just a few minutes. So for the exam, it covers all of chapter 1 and chapter 2, except for the reading sections that you were told to skip, like the random temperature scale differences and stuff. And we're not really focusing on a chapter right now. I'm introducing the new tables. So I'll tell you what page those are on when I introduce them. Other questions? Okay. So going to get out my whiteboard. So this is kind of a brief review slash segue into a little bit of new information. And we're looking at, if we look at internal energy, we know that internal energy is defined by this letter U. We've been looking at it for several weeks now. This is a capital U because I'm looking at internal energy, not specific internal energy, which is a lowercase u per mass unit. And if we're looking at our change in internal energy, we have this change in internal energy, or a du, which is the same as like a delta U, right? But this is like a calc nomenclature. And we know our change in internal energy is going to be our internal energy at point 2, or our final point minus our change in our internal energy at point 1. This is our change in internal energy. We haven't really looked very much at the equations associated with internal energy yet, except for fluid flow. But there is another equation, and if you take my fundies class, you have seen something similar to this before because it involves a concept of specific heat. So if we're looking at our change in internal energy, this is going to be the same as the integration from point 1 and point 2 of the specific heat at a given temperature and the change in temperature, where the C value represents our specific heat term. Oh no. Thank you. Okay. Sorry, I'm trying to figure out if there's a good page to look at for this. Okay, so starting on page 933 in your textbook, there are several tables that have tabulated the specific heat for different gases at constant pressure or constant volume, along with these on page 937, specific heat values for common solids and liquids. So on page 933 and 937, you can look up these specific heat values. They are obviously specific to the type of substance that they are associated with. And specific heat is the amount of energy required to raise 1 unit mass of a substance by 1 degree Celsius. So I already have defined this in my fundies class, so that should sound very familiar for you. But for those of you who aren't in my fundies class, we have specific heat. And it makes sense that it's specific because it's per a unit mass. We represent this with a letter C. This is a lowercase c because it is a specific unit. But unlike internal energy or specific internal energy, we don't have like a total heat represented by an uppercase C. That's where we start to get into enthalpy and some other terms. So specific heat is only ever going to be specific heat. Specific heat is defined as the amount of energy required. Amount of energy required to raise the temperature. The amount of energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius, of a substance by 1 degree Celsius. Change the way these are. A substance by 1 degree Celsius. So Abed, I'm not sure exactly what edition of the book you have, but this should be labeled as table. You can look this up in your index, table A-3E. The 9th edition, it should be, yeah, these are index page. Oh, it shouldn't be an index, it should be an appendix. So this should be appendix 2, and it should be table A-3E and A-2E. And these are in appendix 2. So they might just be a few pages earlier in your book, but they should be there. I would just look for these table numbers, especially if you're already in the index, you can just figure out what page those are actually on. But I'm using the 9th edition, so that's kind of strange. Okay, so this is our term for specific heat. For one thing to note, it's not going to be very important in this class, but we have specific heat with the subscript V and specific heat with the subscript P. Specific heat with the subscript V is the specific heat at a constant volume. So specific heat at a constant volume, at a constant volume. And this is specific heat at a constant pressure with C subscript P, specific heat, constant pressure. These are only relevant to gases. For solids and liquids, for liquids and solids, C sub V and C sub P are equal, and we just denote them as a C. If we come back to this integration here, we have our specific heat that's a function of temperature, and our dT term, our change in temperature from points 1 to point 2. If we assume that our specific heat is relatively constant over an average volume, this equation becomes our change in internal energy is equal to our specific heat average times temperature at point 2 minus temperature at point 1. And this should have units of kilojoules per kilogram, which makes sense for a specific energy term. And this is your average specific heat, which you'll get from a table. Typically, we kind of ignore this average as well. We say that, you're looking at a certain system at a certain temperature. We're going to assume about this temperature for this specific heat. That's what value we're going to look up. So a lot of times this specific heat term just becomes your C term, not just a C average. So this is an equation that we're going to start using for internal energy instead of the fluid flow one that we've used, or instead of canceling it out. We are going to start paying more attention to internal energy. As I mentioned, these, yes, this is a lowercase u because it's per kilogram. Will I give you specific heat capacity for water yeah. So if I'm working this, if you're expected to work this on an exam, I will either give you a list of specific heats on the formula sheet that's attached to the exam, or I will give it to you in the problem statement. I do think that it's probably worth your time to memorize the fact that the specific heat of water is 4.184 kilojoules per kilogram degree Celsius, but I would give it to you because that's not on your memorizables. Okay. So here's an equation that we're going to start using for internal energy. Are there any other questions? And this is a lowercase u. Great. Anybody need more time writing? Okay. Another term that we have seen before in this class and in fundies, whichever fundies you're in, is going to be enthalpy. So enthalpy is represented by this H term, and it is corresponding to the heat content of a system. So in fundies, you've probably seen the delta H equals H of the products minus H of the reactants, which is great for environmental chemistry and for chemistry, but it's not super relevant for thermo. We're only really interested in enthalpy that's related to internal energy and pressure. So we have another equation that we use more commonly. You have also seen this in fundies. You've probably seen this in physics or chem as well. But we have this specific enthalpy is equal to our specific internal energy plus pressure times volume. So here we have specific enthalpy, which is our heat content, is equal to specific internal energy plus pressure times volume. And these are in units of kilojoules per kilogram. Sometimes you'll also see these in kilojoules per kilomole, but right now we're going to be working with kilojoules per kilogram. Does that say heat content at the beginning? Yes, this says heat content. It looks like heat content, like heat is happy, but it's heat content. Yeah. Okay. So a lot of times we're interested in the specific enthalpy or our change in specific enthalpy, which is going to be our change in internal energy plus our change in pressure times volume. These are all deltas. And we know from what I just wrote that our change in internal energy is also equal to C average times the change in pressure, right? Just substituting in this internal energy term here, plus our change in volume, change in pressure times our volume. And for many solids, note here, a lot of times your change in pressure is equal to 0 for solids, which makes sense, right? If you have like something like a sheet of metal, you're not really having a strong change of pressure in that metal. So your delta H term also becomes just this C average times delta T. So you can see how important specific heat is as a term. It's also common for not all the time, but common for delta P to equal 0 for liquids. We pressurize gases the most commonly. Solids, we never really pressurize. Liquids, it's not as common. In chapter 5, later, we will look at pressurized liquids and nozzles and hoses and stuff. But for right now, a lot of times you can also have your change in pressure. I should have made that a little bit more clear. Your change in pressure can also be 0 for many common liquid questions. Which this is kind of analogous to what we were doing on Friday, where if you don't really have any pressure drop, especially for like air blowing through a fan or liquid running through a turbine, you don't have this pressure term for a lot of basic liquids and solid systems. Okay, so these are looking at specific enthalpy and specific internal energy, but remember we can have both of those as just enthalpy and internal energy. And we are going to start using enthalpy and internal energy a lot more than we have in the first 2 chapters, starting next week in chapter 3. So make sure you understand the nomenclature here and you know both of these equations are in your notes. Okay. So we care a lot about enthalpy and internal energy in this chapter because of property tables. Property tables are what we're going to start using to solve problems, starting in chapter 3. And we use property tables because enthalpy, internal energy, and entropy, which is this S term. So enthalpy, internal energy, and entropy cannot be measured directly. Cannot be measured directly, like temperature, pressure, or volume. So if you want to know the temperature of something, so Layla, this was asked at the beginning. this is just a brief introduction to chapter 3. This is not going to be on the exam, but you should know internal energy for the exam. Not that equation with specific heat, but you should understand kind of these terms. Okay, so if you want to know the temperature of a system, you can just measure the temperature, you can measure the pressure. But things like enthalpy, internal energy, and entropy, you can't directly measure them. We need to use these property tables where we have kind of scientifically somewhat measured them, created graphs, figured out values empirically over hundreds of years. And now we have these tables where we can look up our enthalpy, internal energy, and entropy values. These are tabulated in our property tables, and typically these are going to be in the 9th edition. In my book, at least, they start on page 888 at table A4, which is labeled saturated water temperature table. So if your book is different, find where table A4 is and make sure that your title matches. And then these property tables go on for several pages, including the superheated water page. And then after a few of these different diagrams, we also have tables for refrigerant R134A, which is the type of refrigerant. So it's kind of a model that we use for a refrigerant type system, which is what is used in a lot of cooling towers. It's used in your fridge in your house. It's used a lot of times in air conditioning systems. It's a type of liquid that has a very different internal energy enthalpy values. So we really only look at water and refrigerant for our property tables. And as you can see, looking at a property table here, this is table A11. It's for refrigerant 134A. And looking at these property tables, you can see that across the top, we have a lot of different variables. And then we have all of these different numbers that are tabulated for these tables. So across the top, we have, first we have temperature in degrees Celsius, and we have P sat at kilopascal. These are easy to understand because it's temperature in degrees Celsius and our saturation pressure in kilopascals. So those are pretty easy to understand. But then we also have these terms here where it is specific volume, which is, I write like this, but if you can understand your lowercase volume better, but I learned last year that students had a hard time distinguishing between this and this. So I started writing it kind of spread out like this and noting an S on here. So we have the specific volume term with a subscript of F. And we have a specific volume term with a subscript of G. And for these nomenclature, our F here is our saturated liquid specific volume. Saturated liquid specific volume. So volume per unit mass. And F sub G is saturated gas specific volume. Specific volume. So this becomes really important nomenclature. When we see a sub F like this, it means that it is 100% liquid. We have, if we are looking at a water vapor, maybe you're taking a shower in a closed box. If you, before the steam gets there and you have 100% water, your entire specific volume is just this fluid term. It's a saturated liquid. There is no gas associated. There's no phase except for liquid. And then conversely, the saturated gas specific volume is saying we have 100% gas. So here is where, if you're boiling water and you leave it on too long and all of it turns into water vapor and you have no more liquid, then you're at this saturated gas specific volume. So saturated meaning entirely gas, entirely liquid. But we do have, let me make sure I write this the right way. Okay. So we do have this term that we're going to start seeing, and it's not tabulated. Oh, that was not good. So we do have this term that we're going to start seeing, and it's not tabulated, where we have this specific volume FG. And this is your specific volume for a liquid and a gas. So liquid gas specific volume. Here's where you have some liquid and some gas. This is a very common thing that we're going to be calculating, because a lot of systems aren't entirely liquid or entirely gas. There's some combination of both. And as you can probably guess, the specific volume of your F sub Fg, your liquid gas, is going to be a value that is between these two values. So if you look in the table, your V sub F and your V sub G kind of create these bookends, and your V sub Fg is going to be a value in between those. So it's going to have a little bit of liquid, a little bit of gas. You need to figure out where in between those two values it occurs. And we will look at that more in week 3. Right now, I'm really just trying to introduce you to the nomenclature so we can hit the ground running during next week in chapter 3. Okay. Is this one saturated? Sometimes we call it saturated, sometimes we don't. I don't think that that nomenclature matters as much, but yeah, I would say this is saturated because we're looking at saturated water. You can add saturated or not. I don't think it's super important for the liquid gas one, but saturated liquid gas is just as correct. Okay. Other questions? Okay. So the next set of terms in here is this lowercase u sub f, lowercase u sub g. And this one, we actually do have a lowercase u sub fg. I'm still on page 888, looking at the top row of my property table. So here we have the same nomenclature, but this is internal energies for a saturated liquid, internal energy for a saturated gas, and this is internal energy for a liquid gas mixture. We have the same nomenclature at H sub F, H sub G, and then there is an H sub Fg, where this sub Fg is in between these two terms. So it follows the same pattern for specific volume, internal energy, enthalpy, and then we do also have an entropy term here, but we're not going to look at that for several more chapters. So by then you should be very comfortable with this nomenclature. For those of you who have your book, I want you to just take a moment and look at, say, the very first temperature line, temperature at 0.01 degrees Celsius, that first line. And if we look at enthalpy, H sub F, we have 0.001. And if we look at enthalpy for 100% gas, H sub G, we have 2,500. And then if we look at that H sub Fg, it should be a value between those two, but you can see here that it's almost exactly the same as the saturated vapor, H sub Fg. And then as you move down the table, this term gets lower and lower. The values will change, but this H sub Fg term here will always be a term that's between this H sub F and this H sub G. So 100% liquid, 100% gas, a mixture is going to be somewhere in between there. All right. Are there any questions? So I know you're probably focusing on the exam right now, but make sure that next week you understand what I mean when I say a saturated liquid, a saturated vapor, or a saturated liquid vapor, what these terms mean and where to find your property table, because I'm not going to go over that again. I'm going to say, okay, in the property table, we can find internal energy of a saturated liquid. We can see the value is this. And so you should know what that means. Okay. One thing that is important to know how to do, especially when we are looking at these big tables, is interpolation. A lot of people have a lot of different ways that they like to do this. If you already know how to interpolate, do what you feel comfortable with. I'm going to show you the method to me that is the most step-by-step. It's not always the method that I use, but I think it's the method that's easiest to teach. So interpolation is what we use. Okay, so to find a number in between two other numbers. If we look at this table, we have temperature like going all the way down for all these different values. So we have temperature at, let's say, 65 degrees Celsius, and then at 70 degrees Celsius. But what if your system's at like 68 degrees Celsius? How do you figure out your values? And the way that you do that is by interpolating. You use your lower bound and your upper bound, and you figure out proportionally what that means for your values in between. It's really easy when you're exactly halfway in between, but it gets a little more complicated when you're like, whatever, 66% between your lower end and your upper end. So we need to do interpolation, which is pretty much just basic math. So for this class, I do linear interpolation. It's all you'll really need to do. If you take advanced math, you'll do different types of interpolation, but not here. So for interpolation, I think it's easiest to explain it as an example, but the equation that I use is y3 is equal to y1 plus bracket x3 minus x1 over x2 minus x1 times y2 minus y1. So when I'm talking about y1, y2, and y3, I'm going to have some property table where I have points such as x1 and y1, x2 and y2. And I'm trying to figure out some value in between here that I'm calling x3, y3. For instance, if we had a temperature chart, and we had this in degrees Celsius, we have 10, 20, 30, 40, and 50. We have some corresponding pressure. Golly, this is not writing right today. Pressure. We're going to do this in kilopascal. And for 10 degrees Celsius, it's 0.5 kilopascal, then 1 kilopascal, 3 kilopascal, 5 kilopascal, and 7 kilopascal. And we want to figure out what is the pressure. What is the pressure at 37 degrees Celsius? So we want to figure out what is this pressure in here at 37 degrees, and what is the corresponding pressure over here. So here we know that our lower bound, our x1, y1, is going to be this 30 degrees, which is 30 degrees and 3 kilopascal. And we know that our upper bound, which is x2, y2, is going to be 40 degrees and 5 kilopascal. And we want to try to figure out what our x3, y3 is, where we know that x3 is going to be 37 degrees. We want to figure out what this y3 term is. Okay. So using this equation here, I think I'm going to run out of room, but we want to use this equation. And we know that we have y3, which is what we're solving for, trying to solve for, is equal to y1, which is here, 3 kilopascal, plus x3 minus x1, 37 degrees minus 30 degrees, over x2 minus x1, so 40 degrees minus 30 degrees, 40 degrees minus 30 degrees. And then this is all going to be multiplied by y2 minus y1, which is 5 kilopascal minus 3 kilopascal. These degrees Celsius here are going to cancel, and we're going to be left with kilopascal. So this becomes 3 kilopascal plus 0.7 times 2 kilopascal, or 1.7 kilopascal, which gives us 1.7 kilopascal plus 3 kilopascal is 4.4 kilopascal. So does that make sense? Is that value kind of what we think it would be? And does everybody kind of understand how I got there? Yes, okay. All right. So there are a lot of different ways to do interpolation. If you're good at proportions, you can probably figure out ways to do it easier. I think this is the most like step-by-step method. But if you have another way of doing it, like feel free. You don't have to do it this way. There are other Khan Academy videos and videos online that help you figure out how to do linear interpolation as well. So whatever you feel the most comfortable with. All right, so I want to do, does anyone need more time writing? Okay. Oh, sorry, Levi. I'm going to post these online. So if that was the yes for that, I actually think that was an earlier yes. So, okay, great. But I'll still post these online. So I want you guys to try this. Here's an example. This is similar to what we're going to start doing in a couple of weeks. So here we have pressure, which is in kilopascal. We have pressure at 25, 30, 35, and 40. And then we have saturated water vapor enthalpy, so H sub F, so saturated water vapor enthalpy, or saturated water enthalpy. And these values are going to be 104.83. So this is what it's going to look like in a table if you're just isolating pressure and this enthalpy term for saturated water. And here we have 125.74. This is still, well, this is just from the table, but I'm going to ask you to do interpolation. Right now, I'm just copying down the table. The solving of it is interpolating. Yeah, if you're finding values between certain values using that equation, it's called interpolating or interpolation. Okay, so 125.74 and then 146.64 and 167.53. And these are in kilojoules per kilogram. And what I asked people to do last year. All right, so find your specific enthalpy of a saturated liquid for, let's say, 29 degrees Celsius. So I'll let you work on that for a few minutes. Type in the chat once you think you have an answer, and once we have enough people, we can move on. Yep, sorry, 29 kilopascal. 29 degrees Celsius is not a pressure. Please make sure to enter in the chat whatever you get, just so I can gauge how many people need more time. Yeah, good job, everybody. Great. Okay, it seems like several of you are good and you understand. I didn't see any incorrect answers. Is there anybody who's still confused? Anybody who maybe didn't get the right answer or struggling to figure out what to do? Okay, well, if you want to tell me later, because maybe you don't want to say out loud, that's absolutely fine. But yes, so your HF value would be 121.6. Make sure you're including units, kilojoules per kilogram, or 5.6. So great job, just using this equation or whichever equation works the best for you. What if you were given a system that looked like this? You have temperature in degrees Celsius. So you have 175, 180, 185, and 190. And you know your specific volume for a saturated liquid is, and this is cubic meter per kilogram, because we have specific volume. And your value here is 0.001121, 001127, 001134, 001141. So these are actual values from the table. I'm not making these up, I'm pulling these from the table. And what if you were asked to find temperature when your specific volume of your saturated liquid is equal to 0.001131 cubic meter Kelvin, or I'm sorry, degrees kilogram, or no, kilogram, not degrees kilogram, cubic meter per kilogram. So try to solve this, where now we're looking for our X term and not our Y term.
So for this one, I probably wouldn't do the same thing, but I was wondering if the last one I got the correct answer with a different way. I did like, because it was 29 pressure and there was 30 and 25. So I did 4/5 times the pressure at 30 and 1/5 times the pressure at 25. I mean, for this one, I probably wouldn't do it because it's harder to find the proportions, but that's valid, right? Like I want to make sure it wasn't one-off thing. Like,
no, that'll work as long as those proportions are right. So if you can break it down into fifths or quarters or thirds, that'll work. but sometimes you can't break it down into like, 3/18 or whatever, like depending on how far spaced they are. But those proportions will work. Yeah, that's the like kind of logic behind why it works, is like we are just finding the proportions.
Okay, thank you.
Other questions? Dan, you're fast. Yeah. So write it in the chat when you get an answer or if you have any questions. So anybody need more time? Maybe you just didn't feel like answering in the chat. Anybody still working? Okay. So Kat, I'm not sure. It should definitely be a value that's between these two. So 177 doesn't really make any logical sense, but I think one of the issues, make sure that instead of having this as your y value and this is your x and this is your y, you're going to switch. And so this is your x and this is your y, because you're looking for this unknown over here. So you're going to have well, you can kind of see where this falls between, right? It's going to fall between 180 and 185. Yeah. So you don't need to manipulate the formula. I would just go with, this is your known. So your x1, y1 is going to be 0. This is your lower. So 0.001127 and 180. And then your x2, y2 is going to be 0.001134 and 185. And then you're solving for x3, y3. And your x3 is 0.001131, and you're solving for this using the same equation. So your x's should always be the one where you know all three of them, and your y should be what you're solving for. So just because it's listed in a certain order, you should double check what which should actually be your x and which should be your y, and your y should always, this third y should always be your question mark. So I think that's probably where the math error came up, and that's why I give this example to kind of like not trick you, but show you that you need to know how to flip them. Great, good to hear. Okay, so is anybody still working on this or need more time? Okay. Okay. I'm going to go ahead and move on. I will post these so you can make sure that you have the right answer. For this one, the answer is 182.9 degrees Celsius for this specific volume. If you were solving a problem and you were told that you had a 1 kilogram tank that is 40 cubic meters that held some sort of solution, and it was being heated up to a certain temperature. Remember that you can always find specific volume. Specific volume is volume per mass. So if you're given a volume and you're given a mass, you can find your specific volume that way. So in a lot of problems, you won't be given specific volume. Sometimes you will, but sometimes you'll be given volume or mass. If you're not given, if you're given specific volume and you're asked to find volume or mass, always remember this equation, right? So if you're given specific volume, you can always figure out, you can try to back out a mass or a volume term. So remember what the definition of specific is, because a lot of times we're going to need to use our specific volume term to figure out either volume or mass or vice versa. So don't forget what the definition of specific is. Abed, you're a little bit off, but I can go over it with you maybe office hours or later, or you can check yourself, and we can do that later. Okay. So I'm going to save this, save it, and clear it. Okay. So for the last new information I'm going to present today, and then on Wednesday, we're going to have a review. Friday, we're going to have the exam. There are a lot of new terms in Chapter 3. So Chapter 3 brings up a lot of new, like a lot of Chapter 3 for the first part is text, just words. And it is not a good use of my time to give you definitions. So I'm going to tell you the words that you need to know, and I'm expecting you to read the chapter and learn the definitions on your own. They're not tough words. They're just like a certain jargon. So these are Chapter 3 definitions that I would like for you to know. I will just start using the words, and I'm expecting you to know them because it would take a lot of time for me to go through and define these individually, and it would be mind-numbingly boring. So I hope that you can read the chapter, the beginning of the chapter and some of the definitions. You can also look these up online or look them up in the back of the book. Make sure that you're looking these up if you look them up on Google in relation to thermo. Okay, so the first one is incompressible fluid, or even just incompressible. I'll say incompressible substances. What does incompressible mean? What is saturation pressure? Which is P sub sat. What is saturation temperature? T sub sat. What is latent heat? What is a critical point? What is critical pressure? P sub CR. What is critical temperature? T sub CR. And what is critical volume? V sub CR. What is a superheated vapor? What is a saturated mixture? What is a compressed liquid? What is a saturated liquid? Oop, there's not a dot there. Saturated liquid vapor region. Okay. These are ones that you need to know. We're going to start using them in problem solving soon, starting next week. So I'm actually going to end class a little bit early to give you time to go to chapter 3 and try to write these down now. So you don't have to take time away from studying or your weekend or anything. So I'm trying to leave about 10 minutes for you to be able to do that. And then try to review them again before class on Monday, because I'm just going to start saying, all right, well, we know our saturation pressure is this, blah, blah, blah. And you should know what saturation pressure is. We're going to look up our T-sat in this table, blah, blah, blah. You should know that I'm referring to saturation temperature and what that means. In particular, we're going to use the saturation pressure and temperature, and then these superheated and saturated terms the earliest. So make sure you're comfortable with those. Okay. Are there any questions about anything? Exam is in person. You need to wear a mask. Separators will be up. You will be spread out throughout the room. You do not get a formula sheet. I give you a formula sheet. You're allowed to bring a calculator and your pencil. I will be doing a review on Zoom on Wednesday during class time. It will cover chapter 1 and 2, along with all in-class activity, problem solving, and homework problems. And if you are unable to attend on Friday in person due to COVID, let me know. I will schedule a makeup exam for you to take in my office, or the exam probably within a week or two. depending on your quarantine and depending on how many people. So exam Friday will be in person and makeups will be in person. Any other questions? Okay, so there's 15 minutes left in this class period that you should have allotted. So I want you to spend those 15 minutes looking up these definitions in chapter 3 or in the back of your textbook. So make sure that you look these up now, you read them over, you know what they are, so we can start right away using the property tables and solving problems next Monday. Join me on Wednesday for an exam review, and then join me in person on Friday for the exam. Any final questions before I adjourn? Okay, just to summarize too, you don't need to interpolate on the exam. You don't need to do any specific heat on the exam. This is all going to be energy, work, efficiency, your memorize things, all chapter 1 and chapter 2, unit conversion, those things. So what I went over today is not on the exam for those of you who missed that at the beginning. All right, well then I hope everybody has a good day. Work on the definitions now, and I will see you Wednesday for an exam review. So bring any questions that you have on Wednesday as well. So I'll do a little review and then I'm gonna be taking questions. So
bye, thank you.
Yeah, bye, have a good one. Have a good day. Dan, do you have any questions? Okay.